camera. And one of the good things about just recording, I noticed that when I just looked at myself from the camera and I said, oh my god, I'm getting totally bald. Then that's one of the things with the camera which I discovered about myself. Because the camera just on the top of my head. Oh my god, I'm losing my hair. Okay, now, guys, yesterday, any questions about the topic that we had yesterday? Anyone, any questions? The people who were absent, I hope that you got a chance to check their coding, because we did a very spectacular job that we proved yesterday. It was a very, very spectacular job that we proved yesterday that there is only one function through the whole universe that you can think of, and that function is e to the power of the x. But what was significant about that was that this function, if we say that, how is that going to change over time? With respect to the changes of the x, it says that, no changes at all. It seems that, imagine that e to the power of the x is like the human beings. It never gets old, it never ages. It always stays young, never changes for that function. And that's the only function in the whole universe. It changes, it's always zero, always remains the same. And for people who were absent yesterday, we did a very spectacular job, all of us together, to come and to prove this, showing why that happens. And in order to show that, we just needed to use this definition of the e to the power of the x. And we said that if, for example, someone gives you this limit, 1 plus n to the power 1 over n, and they say that your variable, it can be x, your variable goes to 0. For example, 1 plus x to the power 1 over x, x goes to 0. 1 plus apple to the power 1 over apple, apple goes to 0, anything. This, it gives you close your eyes. You do not need to prove it at this stage. You close your eyes, you lean back, say, I do not need to prove it. It's just the Euler number or the natural number. And that's the thing that we use this one in order to prove that e to the power of x is gonna stay young forever, no changes for that function. That's essentially what was we did yesterday. And I hope that if you have any questions in how to just get to prove this formula, either we can talk, or you can check the videos, and we just had a elaborate discussion on yesterday. Now, today I'm just going to erase this one, and we just do some kind of, I should say, very interesting problems. Okay. The first problem that I'm just going to do is that this is a kind of a popular exercise that we do in the calculus. And that's, you may guess, it's going to be, I say that there is a popular exercise in calculus, and you're going to ask me, is it the problem of the tangent line? If that's what you're going to say, I'm going to say yes. You're going to do a popular exercise. And that's for the tangent line. We say that we have a functions, for example. This is going to be e to the power x and x to the power over x to the power 2. Now, we can just plot this function. We can just plot this function and see, for example, how it looks, but we do not need to do that. We are just going to find the tangent, the equation of the tangent at the point, for example, where x is equal to 2. That's what we want to do. Based on the things that we have learned so far, Arma, we have learned that when you just want to find the equation of the tangent line, you need what? For example, if, let me just use different colors. For example, if this is going to be your f of x, and when you're looking for the equation of the tangent line, For example, at this point, which is going to be this, we said that it comes with an equation ax plus b, and that was a point essentially, as you remember, that we were able to connect the slope of this tangent line to our analytic solution, which was a derivative. We said that a, the slope of the tangent line, which is the tangent of the angle, which also equals the derivative of the function at the point which I called it x naught. That's what we covered sessions before. Now, then you say that, okay, then if I just want to find the equation of the tangent line, first of all, I have to find the slope. Finding the slope, Tommy, is going to be very easy. We said that in order to find the slope, which is a, it means that I have to find, it was an analytic interpretation of the derivative, that we have to find the changes with respect to the variable x of the function which I'm looking at, e to the power x over x squared. That was the first thing that we have to do. The result of this, evaluated at the point that we are just focused at. This example I said x naught, but we know that for this function it has to be at x equal to. Then when you find this one, you substitute 2 in x, then you find the slope, and essentially you have the first parameter that you're looking for in the equation of a tangent. Now the problem is that you say, oh, I have to find derivative of this one. If you have started a beautiful day so far, it's gonna make your day even much better. Because you remember you have two methods to find the derivative. The first one, Tony is gonna just say, okay, the first one which I'm gonna use is this method. Let me erase. And I love this class because as soon as I write something, I have to erase it. The board is too small. The first method is this. I say, okay, I'm gonna look and focus on this function, and in order to find the derivative, I say, okay, look at this. I have this term, which is at the denominator. Then I'm gonna take it up. Then I say that a equals to d over dx of e to the power x times x squared. Right? That was the first method that we learned initially. Yes. That's right. Thanks. X to the power minus 2. Thanks for correcting me. Still, I haven't had my coffee in the morning, and that's why you see these kind of mistakes. Now, thanks, Tom. Now, I have this one. That was the first method. We take whatever is down there to the numerator and find the derivatives using the product rules. However, we also learned that in order to find the derivative, also we can say, I keep this one here, d over dx, of e to the power x over x squared, and I use the quotient rule. Two methods we know that we can use in order to find the derivatives. Any questions so far? You missed it, Cyrus, huh? Next time you're gonna do better. Practice make it perfect. Oh, it was too far off. No worries. Okay. Now, while Cyrus is gonna do the practice during the 1 minute stretch, now let's see. For the first one, we have this function. We know that from the product rule. In order to find the derivative, what do we have to do? We say that. Any questions so far? Everyone is clear why do I have two different methods? The product rules and the quotient rule. Now, for the first one, it's going to be very easy because I said that. The derivative of the first function times the second function. Let me write d over dx of e to the power x times x squared plus e to the power of x d over dx of, again, x squared. Okay, now, first of all, let's substitute everything in there. What is the derivative? Yes, but yes or no? Why I keep writing it x? Thanks. I don't know why I keep writing 2. Okay, now, what is based on the things that we have learned? What is the derivative of e to the power of dx? Anyone? Yes. That's so true. The derivative of e to the power of dx is e to the power of dx. Yes, Sebastian? I can see. You have a question, Sebastian? You're fine? Awesome. Awesome. Thank you. Now, I said that this is going to be e to the power of the x. It is multiplied to x to the power minus 2. Ah, I got it this time. Plus. Now, look at this. Plus e to the x to the power of the x times what? The derivative of x to the power minus 2. Now that's the power rule. What is that term? You take minus 2 times x minus 2 minus 1 becomes minus 3. Check the power rule that we had before. Now, look at this. I'm just going to write, I hope everyone can see that. You see that e to the power of the x is a common factor. It's okay so far if you are there. But sometimes I like to just explicitly show this never getting old function, e to the power of the x, and factor it. From the first term, I have x to the power minus 2. From the second term, I have minus 2, x to the power minus 3. Either of these is good. Now, you say that, what is the slope? You put 2 in there, then you simplify that, you get the slope of the tangent line. Now, I hope the people at the very far back, they can see what I'm going to write here. Did everyone see this? Yes? The second method is going to be much easier. Look at this. Yes, you have a question? No? Now, this method was a little bit more detailed, and it looks so pretty, especially with different colors, which I have done. But now it's too much work. Now we just go to the quotient law. Quotient law is very easy. We just covered that on a couple of sessions ago. And we said that. I'm just going to write it in red to make it separate, to look separate from the top. We said that from the quotient law, sorry, it's getting too down there. I hope that you can see. We said that for the quotient law, we say that we take first the denominator goes to the power 2, which becomes x to the power 4. We said that the derivative of the numerator, which is d over dx of e to the power of the x, multiplies to x squared plus, minus the derivative of the denominator, d over dx of x squared times e to the power of x. Now, if you cannot see that, you can just come to see any of these two seats. I have 2 VIP seats, the first VIP seat and the other one there. It's VIP seats. Now, for this one, you see that on e to the power x, the derivative becomes e to the power x. Then I have x squared times e to the power of x. I have minus 2x, or minus 2. Look at this again. No, it was correct. It was correct. This time I was correct. To the power 2, because the derivative of this time, yes, minus derivative of this times this. That's correct. Now, it becomes 2 times x times e to the power x divided by x to the power 4. The first VIP seat is taken. I have one more VIP seat left, if you are interested to join us. Okay, now this is shown on. Now.
Yeah.
Okay. Huh? Okay, guys, look at this. Now, I have this one there. I reached to this last term. Is it good now?
So why is it the denominator x to the 4?
Because in the quotient law, we said that the denominator goes to the power 2. X squared times the power 2. That becomes x to the power 4. I eventually can write it there. Look at this. It was a quotient law. We said that d over dx of function f of x over g of x, that's the quotient law. Becomes g of x, you keep it down there, but it goes to the power 2. Then you say that gx times derivative of the function at the numerator minus f of x d over dx of g of x. That's the quotient law, which I use it for the second method. And that's why you see x squared. Now this is x to the power 4. Now, and you see that, it's getting too nasty getting there. I divide all terms by x to the power 2, and I take it go up there. Then becomes x to the power 2, with x to the power 4 becomes how much? That's right, I take it up. I have x to the power minus 2 times ex. And this one, minus 2 times x to the power minus 3 e to the power x. And you can compare this. Look at this term. If you factor e to the power of the x, it's going to be the same term. You see this? Then from those two methods, we were able, I'm so sorry for the people at the back. Let me just not to see. Let me simplify. You guys down at the back, it's not much tired. Now, you see that from two methods, we got the same slope. You plug 2 in either of these two formula, simplify it, then you get the slope of the tangent line. And if you want more details on this, you can go to your handout, page number 231. It has more details in there, and you can find more, I should say, numerical values. But the response which I have on the board, it covers two methods to find the slope. On the text that you have, there is only one method to find the slope. Then I recommend you just write everything in there when you go back home to compare this with the solution on your handout. I'm so happy about today. You did a very great job. Yes, Sebastian?
Yep.
Any questions? Any questions? No one has a question? Don has a question? It seems no. Are you sure? Okay, guys, if there is no questions, you can just spend 1 minute to do some stretch break. Talk to someone who's next to you. And silence, you can keep practicing the targeting the beam.
I'm like, no.
What? Oh,
Feel better?
I am. How do you get here? I don't know how to
get back to the normal Friday. You know, we had a little
Easter? Well, I'm square 0.
Get started. Okay.
Oh, phenomenal. Absolutely. No, I really felt like this speech is directed at me.
I felt like there's
I got a 2 out of 10 with 130 words. In my books, if I do the full thing, I have 390 words and I get a 6 out of 10. Right? So if I'm doing the entire thing, 503 words times 4, 2 times 4, 8 out of 10. For me, that's
not bad.
I don't think it's a 6 out of 10. You know what? I think it might.
And you mean that is
Right. It's all about the proportion.
Oh, wait.
It is.
Bro,
Wait, I think I just
It's just like,
He was like, in some minutes, I don't know what I'm gonna say. Prepare to
and so I would be having a very deep teacher interview anyway, so no need to worry.
Now, guys,
It just show up
you
on
have
the day,
30
just
seconds
like,
left.
just walking around and just say, how's my son? Pretty much. You're on the outline, you got 3.
No, you did get it. Yeah. Sorry, I was doing it in a different one.
I took the quantity and quality of work.
It's just neither were there. Usually it's either quantity or quality, and this time it was neither.
Start getting both.
The period ends
Oh,
what
yeah.
time?
Never get
11. Oh, nice. You have a lot of time.
Also sad.
Right, let's get back to work. Yes.
That one's wrong.
That is wrong.
Oh yeah.
Yes, empty.
Oh,
So I
okay.
got ones on Amazon.
Good. I had it right. My God, that's not too much. It's the one on the left.
$80
Right, please take your seat.
I got cheap with
And I'll never get $80 cookies from Amazon.
Just we'll see how they turn out.
You should always try them on. I can think about some places.
The other thing is very good. The other thing is my feet were hurting so much.
Your feet hurt.
I know,
I lost 3-0.
my feet were blistered.
Okay, now.
We have a -2 goal.
Okay.
Yeah.
Did you ever get black feet?
The black
Guys,
jeans.
Yeah.
I'm working on
please
it.
take your seat back.
I'll get it
The
this
game?
Please, everyone, seat. Take your seat back.
It's the goal. He should have scored.
Tommy, everyone, please seat back.
He missed it.
Is there a shoe this weekend?
Yeah.
Lauren,
Black jeans?
Yeah.
Are you gonna paint them right?
Tommy.
I think, yeah.
Yeah.
So like, not expensive jeans.
Yeah. So I have a pair of expensive ones.
Oh, sorry, please take your seat back.
Tommy, sorry for interrupting. I'm so sorry for interrupting.
Okay, now you're just moving to something very, very interesting now. You remember that we said that, imagine that. I give you a function, for example, like e to the power x. And I give you another function. That's the thing. I'm just going to refer back to the things that we have learned from the Functions 11 course. Now this is a kind of a minute reminder before we move on. We start with the first function f of x. Then for the g of x, I give you something different. For example, I give you square root of x to the power x cubed plus 5. These two functions. A separate functions, independent function, a separate and independent function. You learned from prior years, we can just, have some very interesting game. We say that, okay, I looked, for example, I can just make this composite function, and I write it like that. It means that what I'm going to do is that I say, oh, look at this. Function f has swallowed the function g. It's like the pizza. It tastes like a pizza for f. Then what does it mean? It means that you take the function, you plug it to the x of the e of x. Then it becomes what? E to the power of square root of x cubed plus 5. And it sounds familiar to you all?
Yeah.
Yes? That's a composite function. You take one function and put it as a variable to the another function. Yes, Sebastian? Or vice versa. You can just put f of x in there. Now, If that's going to be the case, we say that, oh, wait a minute. I know by the things which I have learned since yesterday that the d of v of x of e to the power of the x is e to the power of the x. But the question that we may raise is that what is going to be this d over dx of now a completely different function, e to the power of x cubed plus 5. What is that? Do you think it's gonna be again the same function? Because we said that if e to the power of x is a function who is never changing and always remains constant, even though its variable changes, can I deduce from that even a composite function like this is not going to change with respect to the x and always stays young and it never gets old, it never changes as the variable changes? Can I say that? Who thinks I can say that? Let's put it on the board. Who says yes? This is correct. Elliot says yes. Who else says yes? Dom says yes. Then it means that also everyone says, oh, okay, now I love it. You get more courage to say it. How about the others at the back? It means that you say no, it's not correct? Or you prefer not to say anything now? Yes? Now, the thing is that, look at this. When I say the changes of the function e of x with respect to the x remains e to the power of the x, look at this. E to the power of apple, when the apple changes, gives you e to the power of the apple. But now look at this one. It says that e to the power of a melon, when the apple changes, doesn't make sense at all. Then it means that these cannot be equal anymore. Then if you guess that maybe this is going to be valid also, it's wrong. Then this is only true to the power e to the power of the x. But if you have a composite function, that the function is not going to stay young forever. It changes. Now, then you notice that this is not a valid equality. Do you want to come to the VIP seat? You're fine? Okay. Now, the thing is that what I'm going to do right now is that we are going to learn how to deal with this type of functions. I'm going to erase this one. I'm going to erase this one, and now we are just going to develop. Let me erase everything. In order to just develop a kind of a strategy how to deal with this kind of functions, I'm just going to go back to the methods that we somehow learned that implicitly. We said that we are looking at changes of a function with respect to the x, however, it comes with this form. The function is a composite function, and now we are looking at the changes of the composite function with respect to its single variable. We said, okay, we had some sort of similar method to this. We said that the first thing that we do is that we come over here and say that it's going to be d over dx of f of g of x multiplies to derivative of g of x. You may wait a minute. It somehow reminds me of the fact that we had a couple of sessions ago about a baby inside the mother's womb. We said that the baby is kicking.
Yes.
That's somehow similar. Look at that. F is going to be the mom. G is going to be the baby. The mom is running. You want to see how fast? Yes, no.
Yeah.
When they put that in a drawing and the people put it on the wall that they can see it every time. Because I don't like that drawing is gonna erase it. Let's do it.
Me and Dom are very visual learners.
Next time I'm gonna draw it. I love that you use every skills that you have in order to learn better.
Yeah.
I'm so impressed. Now, you see that the F is the mom, G is the baby, the mom is running. You want to see how fast the mom is running. And depending on how fast the baby is kicking inside, the mother's speed is going to be different. If the baby is so quiet, mom can run faster. If the baby is kicking so hard, the mom cannot walk, then the mom is not fast enough. Now, then as a result, what we do, we say that. Then as a result, what do we say that? Guys, please everyone listen. We said that in order to find how fast the mom is running, we said that the derivative of the mom, still with the baby inside, multiplies the derivative of the baby. Huh? Now, I'm gonna give you one example. We had several examples like this. We say that, for example, I give you this function. F of x is e to the power of x squared plus 4x minus 1. Huh? You see that? This function is almost like this example. The mom is e to the power of the x, and the baby is this polynomial or quadratic function. Then Armand is going to ask me, how can I apply this method to this function? D over dx of e to the power x squared plus 4x minus 1. Now, what happens? Yes?
Isn't it just times the derivative of x squared plus 4x minus 1?
That's so true. That's so true. We say that what's going to happen is we say that, okay, now, let me see it. Okay, now, what are they going to do is that, we say that, now, we say, at this time, we say that d of dx of the same thing which we have, the same function, e to the power of x squared plus 4x minus 1. Now, multiplies into d over dx of e to the power of x squared plus 4x minus 1. Now, so far we got that. I applied the rule that I wanted to just find with respect to the thing that we did over there. Now, the question is that, yes.
You just write the same thing.
Now, and that's the thing which I want you also to think of it. How can I get rid of this expression when I use this method of the mother and baby? Give it a minute to think. How can I, just because the first thing, oh sorry, this is not going to be this. This one is going to be g of x.
Yeah.
Thanks for, yeah. It's going to be x squared plus 4x minus 1. Now, because it's going to be the baby, and now this one, it multiplies to this. Now, please give 1 minute to continue from here and try to, first of all, simplify the first term based on the power rules that you know, and find what is going to be the first expression, then simplify that. Take 1 minute and find this one and find this one and multiply it. And you can do that on the board for you. It takes maybe 30 seconds to do that. Please, everyone, you can go and enjoy the rest of the day. Guys, sorry, just, it has to be this one. We take this, look at that. Sorry, I just made a mistake. It has to be, sorry guys. I got distracted myself by my drawing last time about the baby and the mom. I forgot that this one, look at this. You just, for example, you always had d over dx of, let's say, f of x. You see that the x here matches with the rate of the change. This means that also when you have f of g of x, it becomes d of g of x. The same thing, these two should match. Then as a result, this one should be d of x squared plus 4x minus 1. I just made a mistake. I was distracted by my own example. Now things are fine. Let's start from this. In order to find this, you know that the second term, I'm just going to write it here. The derivative of x squared plus 4x minus 1, you learned from the previous course that you are just expanding this operator to act on every individual term inside this expression. Then it means that d over dx of x squared, how much is that?
2.
That's right, 2 times x, 2 minus 1 becomes 1, plus 4x, derivative of 4x over x. 4 times 1, x to the power 0 becomes 4. Derivative of 1 with respect to the x. 0. That's right. Then it becomes this term. Now, look at this. And also this. Now you ask yourself, what is the derivative of this expression with respect to the exponent? If you look at this, do not look at this one, x squared plus 4x minus 1. Look at this one, which I said. Working with this word is so difficult, it's too small. Look at this, we said that if we have a function e to the power of the x, everyone please listen very carefully to this part. If you have 2 i's, borrow 2 more. If we said that d over dx of e of x, let me just put this one x here, and let me just put this one x there. We said that when these two things are exactly the same thing, we can say that it is e to the power of the x. Or, you don't like to write the x, you just want to go very general, you say that d over d, e, and now you say that instead of the x, I'm just going to put, for example, an apple, e to the power of the apple, over derivative with respect to the apple, it gives you the d, e to the power of the apple. You see that everything is the same, it gives you the function itself. If the exponent is exactly the same thing as the changes that you are measuring that. Now, look at this one. You have the same thing, e to the power x squared plus 4x minus 1. Call it a cucumber, for example. And d of the same thing. You see, we go back to the same measurement that we had. Then it means that the whole expression, because the exponent of the natural function is the same as the rate of changes that you are measuring the function with, they are the same, like these two identities, then it means that the rate is going to be the same function, which is going to be e to the power x squared plus 4x minus 1. I'm going to solve one more example in case if you are a little bit confused. Yes, Tom, you look a little bit happy today, happier.
Have you said that this one doesn't equate, like this one equates, like the derivative kind of just, or it rests the same?
Oh, for this one. For the previous example that we had, I'm just going to write it there. The previous example, Tommy and everyone look at this. X cubed plus 5. And Tommy, look at this. This is X. This is apple. This is orange. They are not compatible. But look at this one. Whatever you have as an apple over here, the same expression comes there. Here the same thing. Whatever is there, it's there. But over there, you see that, Tommy. This one, which is as the exponent, is very different than the one that it shows the changes. If this happens, we just use this method.
Okay.
I'm going to solve one more example for this. Then I give you the second 1 minute break that you are probably, you hate that 1 minute break, huh? Because you love to just get more engaged with the math. Any questions? Everyone is fine? Yes? Okay. If you want, talk to someone who's next to you to share some idea about this. Then I'm going to erase it and continue with this one.
You got it? It's just because of D and G,
Right.
Apple. You should have seen my surprise when I looked it up and I saw the TFS to the Apple. E to the Apple.
Yes.
I appreciate it.
So really not learning.
E.
What type of learning?
That's what we are going to do with the change program.
I didn't get it from everything. I was audio. I was audio for the longest time, and then I was it's like you do it about like I say
Square root of and x. Okay, I'm just going to also solve it for you.
I think kinesthetic.
Let me give you the second example. I'm going to write my head and I just solved that part.
I think I want to learn.
I know,
Okay, I'm going to solve it today. Thanks for waiting. That's a good beautiful.
no, auditory is very
Guys, please take your seat back.
It's just the noises.
There you go.
I think I would just combine.
I think I'm a visual learner.
Oh, yes. That just gets the nail on the head, doesn't it?
I think it's the ball rolling.
Okay, before I just solve the second question, I'm just going to ask you a very interesting one, and we are just gonna solve it together. We said that. Learn to ask what is if you have a function which the function is defined like this. You have the ln, the natural logarithm of the variable which is x. And now we said that, okay, now if that's the case, what is the rate of change of this function, which is ln of x? And that's a good example because from the natural number, we can also solve this. Now, look at this. First of all, we see that that is indeed a composite function. The first function is the square root of x, and the other function is the ln of the x. Then when you just want to find the derivatives, what do we say? We say that, before I solve it, you please guys, think of it. Because if I just solve everything, then I'm just making your brain to be lazy. You give it a try yourself. for 1 minute, then we solve it together on the board. Use this method. I did the attendance today, huh? Are you done? No? Let's do it together. Okay, now. Let me, in order to, everyone is written this part? Yes? I'm just gonna erase it and keep that one written. You do not erase it. I'm just gonna write the second method of writing the derivatives. Then that symbol of writing, everyone please listen. This is very important. Then writing that method is going to be very, very much easier. Look at this. Look at this. Based on the things that we said that we get the derivative of f with respect to the g of x times the derivative of g of x with respect to the x. Now, I want to show you another symbol of writing the derivatives. Then I'm just going to use it there. And that notation is just a notation. When we say that d of x of f of x, this is called the Leibniz notation. Sometimes you say that, I don't like the Leibniz notation, I just want to write it in a simpler format. Then you say that I'm just going to write like f prime of the x. The prime on top of the f, it shows that this is the derivative. But that's a different notation. You can just use either the Leibniz notation or just put the prime on top of the f, and that still becomes the same thing. Now, if that's going to be the case, I'm just going to write this one with a shorter format. And I write, in that sense, f prime of g of x times g prime of the x. That's the same thing from the things which you wrote before. I said d over g of x of f of g of x. Instead, it becomes f prime of g of x times d over dx of g of x becomes g prime of the g of x. G prime of x. Now, with this method and notation, then I'm just going to write this one. The ln of x. What is going to be? The first thing which we say is that, okay, by using this method, d over dx of square root of ln of x becomes square root of ln of x prime multiplies times d over dx of ln of x, or ln x prime. It doesn't matter, both are fine. Now, Oh my god, I just went ahead. I haven't found you the derivatives of the natural logarithms. Sorry, I haven't found you that. It's gonna be for next session. I just moved ahead. Oh my god, that's my bad. Guys, please stop here. Tomorrow I'm gonna come back to this. My apologies. Because this one, the d of dx of the ln x, I haven't found it yet. We talk about that next session. Then I cannot solve it right now for you because then you do not know how to solve this. You know how to solve this, but you do not know how to solve this. Because the derivative of the logarithmic function is going to be our next topic. Then my apologies, really. I thought that, I didn't expect that you have to solve this one. Then please, do not erase it from your notes. Keep it there. Next session, we come back from here to solve this. Okay? Yes, ma'am.
You put a hammer in the first.
You mean this one? I put it instead prime.
Oh.
And prime is like the hammer. We say, okay, I don't like to just put the d of x as a hammer. I put only the prime. And these two are the same. Tomorrow, next session that we have to talk about the logarithmic function, you see how this method is much easier. Instead of hammer, we should as a prime. Yes? Good questions, Tom. Thanks. Sorry, my mistake. Sorry. I shouldn't have solved this one. I thought that we covered that way. Now, I'm going to erase it. Now, I want to ask you, please, to just go to the notes that you have. Oh, I distracted the class a lot. Sorry, guys. I thought that we had covered that topic. Just please go to your handout and please go to the part B, page number 233. And there is an exercise there, exercise number 7. And with the remaining time that we have, which is 15 minutes, please try exercise number 7. Then we solve it together on the board. I'm just gonna stop the recording. Oh, that thing is really derailed the focus of me for the course. Yeah. 10 minutes. Okay. Sad. 10 minutes only left. Guys, let's do this together in case you can continue your work, or if you want, you can help me to do this on the test. But if you prefer to work on your own pace, please do so. Otherwise, because we have only 10 minutes left, we have to do this together. Ready? But if you want, we can just continue. I'll appreciate your work. That's so good. Oh, that's good. That's really good. I love it. Thanks. But this one has some kind of problems for this one. A little bit. A minor modification. Review. Good start. Good job, Sebastian. Okay, now, guys, look at this. Now, in order to find the equation of the tangent line, we have to do what? We have to just come and say d over dx. Did I check everyone's work? I think I didn't check for sigma. Did I check for sigma? But that's a very promising work. Minor modification. Great job. You said that. d of x of the full function, which is x e to the power minus x. Now, you see that? Oh my god, that's a product rule. I have x e to the power x. You have two methods to solve it. I'm just going to do two methods. I'm just going to write method 1. It's going to be my method 1. My method 1 is this. I say that this one is going to be, I don't like it like that, I say d over dx of this function x e to the power x. We are practicing product rule and the quotient rule. Because e is to the power minus x, I know that if I just bring it down at the basement, he's gonna cry. He doesn't like to go to the basement. Then it just changes its sign, becomes plus. Then I have this function. Then from the rules of the quotient law, I know that this just becomes what? E to the power x raised to the power 2. The derivative of x times it becomes the derivative of the numerator d of x of x times e to the power of the x minus the derivative of the numerator, which is e to the power of the x. Let me write it in green times x. Does it make sense, everyone? I used everything which I used was the quotient law, which I said the new denominator, it is raised to the power 2. Then I said that the derivative of the numerator, x, times the denominator minus the derivative of the denominator times the numerator, x. Now, I want to simplify that further. What's going to happen? I start from the basement. The basement, it says that e to the power of x squared. How much is that going to be? E to the power 2x. Why? Because you remember a to the power n. Everything goes to the power m, becomes a n m. That's the thing from 2 decades ago which I learned it. Time flies so fast. Now, then as a result, it becomes e to the power 2x. Now, I go to the numerator. I see e. First of all, let's deal with these operators. And as Tommy mentioned, the hammers that we have. First, the hammer acts on the x. d over dx of x becomes how much? 1. That's right, thanks. 1 times e to the power of the x. I have e to the power x minus x times d over dx of e to the power x. I know that the derivative of e to the power of apple, with respect to the apple, it becomes e to the power x. Then it becomes minus x times e to the power x. You can simplify that further if you want. If you are here on the test, it's fine. If you want, you can factor e to the power of the x. You get 1 minus x over e to the power 2x. Then essentially at the end, oh my god, I'm sorry for the people at the back. Then it becomes 1 minus x over e to the power x. I'm sorry for the people at the back. Blame it on the classroom then. Any questions? Please make sure that you take detailed notes. Now, you want to find the slope of a tangent line. You put 1 inside this. Becomes how much? Becomes 0 over e. Becomes 0. It means that the tangent line is parallel to the x-axis.
That's negative.
Do you want me to be in the picture?
But it's negative 1.
If you put 1 there.
Plug 1 into where it says x, so it would be 1 minus 1, which is 0.
Oh, okay. I
yes.
was looking at the wrong thing.
Yeah, no worries. 0 over e to the power E1 becomes 0, it means that the slope is 0, means that the line is parallel to the x-axis. Now, you looked at the question.
Why E to the power times 0?
Now, it becomes, if you put 1 from here,
No, because the numerator.
1 minus 1 becomes 0, 0 divided by E. 0 divided by anything becomes 0. Now we have the second method. We have 10 minutes left.
We have 3 minutes left.
3 minutes.
Yeah.
Oh my God.
Better go quick.
Yes. Method number 2. And please you contributed method number 2 at home. It's going to be the product rule. It means that d of dx of x e to the power minus x, it's the product. E to the power minus x, d over dx of x plus x d over dx of e to the power minus x. That's the product rule.
Oh.
E to the power minus x times d over dx of x becomes 1, becomes e to the power minus x. Guys, look at this. Derivative of e to the power minus x with x, based on the mothers that we talked at the baby, it becomes e to the minus e to the power minus x. Because it becomes minus x e to the power minus x. Let me write it here. Look at this. d over dx e to the power minus x becomes the derivative of e to the power minus x itself, which is e to the power minus x, multiplied d over dx of minus x. d over dx of minus x becomes minus 1 times this, becomes minus e to the power minus x. And that's the reason. Now, you say that, okay, I'm just going to factor e to the power x. Then I get 1 minus x. You take this to the basement, becomes 1 minus x e to the power x. You compare these two, they are equal. Excellent time management. I am impressed. Now, please make sure that you take a note and compare these two methods. When you go home, please compare these two methods. Oh, guys, we had 10 minutes left. It's 10 minutes to
No,
11.
that's possible.
Yes, please, guys, make sure that you learn both methods. Bye.
Thank you.
No problem. Any questions, guys? Send me an email or check the recordings. It's gonna be on the Google Classroom today.
Is the one from yesterday?